Okay, so this thing is still cooking, all right? And I'm thinking that this is the full size of the number right now. But certainly it seems like now I think when my machine's in sleep mode, it's not running. But certainly between last class and today, uh, I've had the laptop open long enough where that number should be bigger. Why do you think it's not bigger? It kind of comes back to our primitive types we talked about, where they hold different size values, right? So let's assume that this is an integer. I'm not sure exactly how we can experiment with it a little bit to see what kind of value is stored inside of an integer here. But when we advertise integers from our C-based languages, an integer is a 32-bit unsigned number, right? Well, so the maximum values that can fit in an integer are -2 billion to +2 billion, which means once this hits that number, it's going to wrap back around. And let's see if we can actually explore that a little bit, since this kind of came up. So we'll go back to here. Let's go ahead and make this guy a lot longer. We'll get Mario away from him a little bit so he doesn't immediately die. And let's just start this and make sure we're okay. So there's our deal cooking. So what was it, around 20,000 seconds? 20,000 seconds is how many? So that's divided by 60. That's the number of minutes. That's the number of hours. So yeah, definitely not cooking since last time. All right, so we have this going like that. Now what I'm going to do is I'm going to start the number at a much higher number. Let's see if we can determine what the maximum size is here. So I'm going to go back here, and I'm going to start off by making a guess that integers, did we do it based on a, yeah, we did it based on the games counter. So at the game level, we put in a variable of type integer called count. And I'm going to assume that this guy, if I'm going by Java rules for integers, these are 32-bit unsigned numbers. So I'm going to say 2 to the 31st power is this. And I'm going to start it at that number, and I'm going to subtract like a couple from it. All right, so that's our starting point. Okay, so it's bigger than that for integer. So I'm guessing it's then 64-bit. So let's do 2 to the 63rd, which gives us this number. Oh, 33rd. Aye. All right. So I need to type that out here real quick. All right, so that's that. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so that's that number. I got to get this. All right, go back into our timer, or go back into our games count attribute. Let's try putting that guy in there. And I'm just going to leave it. So when we add 1 to that, if it's a 64-bit integer, it should wrap to the negative version of that number. Now hopefully this can fit that whole number. Oh, I didn't press oh, that won't fit. Is it some weird number in between? Oh, it'll let me keep typing it, but it won't let it accept it. That seems good. All right, so let's start with that. Will let me accept that? Okay. Let's do a couple more. Okay, wouldn't let me do that. I seriously guessed the correct number of 9s to start with. Total skill. All right, so yeah, what is that? Yeah, but that's like not even based on a power. Well, I mean, we don't know if that's the biggest, but let's just start this and see what happens. It actually allowed it to go bigger. Is this just the size of the text box? I've never actually tried this before. All right, then what we're going to do is we're going to start it off at 0. It might be a limitation of the interface here. Go back to our actors, and the very first thing we'll do when a flaming turtle comes into existence is we're going to change an attribute. We're going to change the flame turtles, the games count to be that. So you got this. Shouldn't that be changing? It'll take too, well, it wouldn't if it's what I'm saying. It should have immediately, as soon as it went 1 bigger, it would have become a negative number.
Well, wouldn't a bunch of those zeros would be different numbers? Because when you copy it from the Spotlight search, so that's not as precise as it could be.
Oh, I guess it's possible. But if this is 2 to the 63rd power, I just need to move this decimal point over 18 spots. So you're saying we're missing some precision out here.
Right. So
All right, let's give it the old college try. Do I not actually have a Chrome window open? Apparently not. This is the number. All right. There. And let's start this at a 5. So after 2 seconds, if it's a 64-bit number, it should wrap around to be a negative number. It's actually interesting that it's showing it in scientific notation. And is it really that? Let's just do a quick GameSalad size of integer. Is it in the documentation somewhere? Doesn't actually tell us there. Integer limit. Yeah, see, it's saying the range is typically plus or minus 2 billion. This is saying it's 16 bits. We've already seen that's not the case. It's a 32-bit. That was certainly helpful. We've already proven that's not right.
Might just be refusing to do the calculation since it knows no wrap.
I would think we'd get some sort of weird game error or something like that if that was the case. Here, let's try to make this a 8. Okay, well, let us do that. That doesn't mean anything. I don't know if we could force it. Let's see. Let's see if there's a function in here. Doesn't look like it. Maybe if we tell it to wrap inside the actor and make the text smaller. No, it still wants to convert it to scientific notation. All right, well, let's see if we can force it, because that's, so we'll just, all right, that should be very big. Just no longer does the math. It could really hold a number that big? It's almost like made up.
Maybe that's how much you can take, and then how much you can enter, and then you can.
Well, when we add 1 to it, though, it should. Here, let's try doing this. Instead of adding 1, let's add that. So we'll start off at 0, and then we'll add 2 to the 63rd to it. At some point here, it has to go negative. If it's not, this is actually very interesting, because then it means it's implementing integers in something called a linked list, which would be horrifically inefficient. That's shocking to me. Every single time, every 1 second, I'm adding 2 to the 63rd power to this number, and it's still staying a positive number. It's just horrifically inefficient to be able to support numbers that large. Well, heck, let's make this extra interesting then. Let's multiply it by that. I just want to see it go negative. Oh, heck, I need to start off 1. Why is it just a 0? It has to go negative pretty quickly here. That or the world ends. One of the two. I think the world ended. You know what? Let me, just to make sure I'm not being stupid here. Okay. I just wanted to make sure it could hold negative numbers. It can. Just, I have absolutely no, well, I do have an idea, but I can't imagine if I put myself in the shoes of the folks who made GameSalad, why they would create integers to be of, let's call it pseudo-infinite precision. I mean, there's certainly a point if you're making a video game, we don't need to deal with numbers that are that big, right? Somebody's game score isn't going to be 15 quintillion or something. You know, we don't need to deal with a game map. You know, let's say you have this giant world, and we'll see later on that what we're seeing right here is just kind of what the humans, what our eyes see at any point in time. But we can actually build out our Mario map way out over here and then have the camera follow us as we're going through here. Even if we consider that, I can't imagine that we're going to need that many numbers on the, I mean, you'd have to have a world that is just ridiculous in size. I'll give extra credit to somebody who can give me that answer. If somebody wants to research it, I'll give you a free quiz. Because that is very intriguing to me. An assignment we do in the 300 class, which is our data structures class, it's 2 classes after this. The class after this is 250, then 300, is we do an assignment on infinite precision integers, where I have you do addition. You create 2 numbers that are infinite in size, well, are capable of holding an infinite size number, and then you have to manually do the math, because the built-in primitive types in the language can only go to a certain size. And one thing that we appreciate from that is, okay, it's possible to do infinite precision until your computer runs out of memory, and oh, by the way, it's really, really, really slow. Okay, cool. So that's the trade-off. If you want to have infinitely sized numbers, you have the trade-off of now everything's super slow. Well, if our argument is game engine should be really fast, probably you put the limitation, you know, the whole matrix idea on GameSalad that the biggest integer you could hold is 32 bits or 64 bits. Not a million bits or whenever this thing croaked on us. I don't know, I want to see that. Oh, I'm still. Let's see if it dies on the negative. It's just fascinating to me. Did the other one die when it was 303 as well? So this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 320 values after the decimal point. How big of a number is that? Let's see, 2 to the 2000th. Oh, that's 2 times 2000. 2 to the 2000th power. Okay, it hits Wikipedia. Okay, that only goes to 660. All right, let's hit Google. 2 to the 2000th power. It's like world-ending stuff. Okay, we saw this. All right, let's do 800. All right, it's 240. All right, we're getting 900, 1,000. Out of interest. Oh, died there. So this is 1, 2, 3, 4, 5, 6. This is 307 places. This is kind of fun. Let's hold on. Let's see, what did we do? We just tried to make a gigantic number in class today. That was the entire class. Where's my clear? Oh, here we go. Let's do 2 to the 2,000. Hey. 2 to the 1,024. All right, the number's too big for Google. I don't know, I just find that really funny.
How much did the power go up each time you multiplied it?
So by 19.
What if you tried putting in 2 to the 1024, like -1, and then or something?
Oh, you mean actually in GameSalad?
Yeah.
Can we? All right, let's. We have to do it this way. We're gonna set this guy to. Where's POW? 2 to the 1,024. Well, let's just try 2 to the 1,024 to start with. So I'm just displaying that for no good reason. So it's, at least we can all agree that that number is larger than anybody wants to deal with. So basically, it looks like wherever we find that answer, it's got to be the one that's one less than infinity in terms of what its math can do. All right, so I can do that.
Could be to create a infinite background.
Well, I mean, I can see some reasons for it, but not at the performance cost. All right, so that worked. 1,020. So let's do 1,023, which would be an unsigned gigabit number. Okay, so let's try to add 1 to that now. Now 1,024 said infinity, right? Just add, here, we'll add 1,000. What point does it become? We're going to add to that. Hey.
It would be 2 to the 1023
Times 2 minus 1.
or times 1023. Is that
We can't multiply it by 2. We can multiply it by like 1.99999. Something like that. That would put it, bring it in just under 2 to the 1024. Huh? Oh yeah, plus, thanks. This class's title is just fun with numbers. All right. So we have something that comes in under infinity. I think so would. Bet you that will come in under infinity as well. So it really seems like it's right around 1,024 bits. There's probably some decision they made in there that makes it so that it's not quite 1,024, but I don't even know. They must have done this as a linked list and just made it. Maybe it's the size of a string. How much they can fit in memory for it. Oh my gosh, it's ridiculous. So it's not actually bound to a number of bits, but effectively it seems like integers in GameSalad are plus or minus 2 to the 1,024 power, which is their gigabit in size. These are gigabit integers, not 16 bits, not 32 bits, but 1,024 bits. Okay. Interesting enough, I suppose. I would have never guessed that they would just decide to do that. You never know when you're going to need the actual calculated number infinity. All right, so let's go back to game count plus 1. It kind of throws off, well, let me actually show you over here in Java then what I was wanting to show you, because this is a common thing in computer science actually. When you're dealing with finite precision numbers. All right, so I'll create an integer called a. We're going to start this guy off at math.pow 2 to the 31st power. And then we'll cast that to an int. Don't worry what that line does. Okay, this takes us to, I'll do a system.out.println a. This should be roughly 2 billion something. Okay, there's our 2 billion something. Now what I'm going to do is I'm going to create a little for loop. We're going to talk about loops today. So n equals 0. Well, actually, let's just do this. While true, let's just print out a, and then we'll say a is equal to a plus 1. Let me actually just do this. We'll make this cleaner. Byte b is equal to 0. While true, print out b, set b to 1 bigger than it used to be. So this would be an 8-bit number. So this is an 8. Stop being jerky. There we go. So a byte is an 8-bit number, if you remember from our notes, that holds the values -128 to +127. That's the full range of values that can be held inside of a byte. So I'm going to start this number off, this attribute, this variable named b. We'll start off at 0. And then I'm just going to go forever. This is a timer that just keeps going, kind of equivalent to the timer we have now. And except in a traditional programming language, with a loop, it just goes as fast as that particular computer can make a loop spin. It doesn't work on a number of seconds like we're able to do in GameSalad. You can set those things up in these programming languages, but it requires some additional steps. So this is just going to print out b and add 1 to it as many times as it possibly can. And what we're going to see is we're going to see b go from 0 to 1 to 2 to 3 to 127 to -128. To -127 to -126 to 0 to 1 to 2 to 127 to -128. It's just going to keep spinning around, spinning around, spinning around. Because once we hit the maximum positive number we can hold in a byte, the next value it uses that first bit as the sign, it rolls over to the smallest negative number. And we'll see this by example here. So see, we get to a big positive number, then it moves to a small negative number, and so on and so forth. So this is what typically happens when we fill up a variable with the most number of bits that it can hold. GameSalad apparently doesn't play by this game. They just, once it hits a final value, it says that it's infinity, which indicates to me that they likely implement integers not as numeric primitives, but instead as strings, as something else, which is fine. Okay, but it should actually mean that those numbers operate slower. But that's typically what happens in programming languages, is when that's when you have to start caring about how big a value is and what it can hold. That gets back to our Y2K problem, where they decided to use 2-digit years instead of 4-digit years to save some memory. Well, you know, in GameSalad, you can just, instead of storing the year, just store the number of seconds since, I don't know, the beginning. I guess, and that's just acceptable. Okay. So in any case, let's get back to our timer here. So this timer is associated with every copy of, let's get back to our game count here, and here, let me just delete this guy. I'll put 2 of these guys out here. And we'll go ahead and run this, and we see that we have both guys incrementing. Okay. Now, this is actually an interesting thing. See, they're both jumping by 2. Okay. It's kind of fun that they're doing that because that's almost somewhat by accident. If we go into Flame Turtle, we see that every single time through this timer, we change count to be 1 bigger than it used to be. Right? It's 1 bigger than it used to be. Well, why aren't these flame turtles showing different numbers? Why isn't it becoming, let's start it back off at 0 so I don't throw myself into a weird loop. So we'll start this guy off at 0. Why isn't one of them showing 0 at the beginning and then the other one showing a 1, then a 2, then a 3, then a 4, then a 5? Because both of these guys are acting independently of each other. They have their own They each have their own timer, and that timer makes a change to the same global variable, to this count that lives up at the game level. All right, so this particular instance of Flame Turtle is going to display the current value of count, which initially will be 0. So it's maybe understandable that they both will show 0 right at the beginning. But then this guy increments it by 1. The other copy will also increment it by 1. But why is it that this copy didn't come back and display the value before the other one was able to change the value? So we have 2 of these guys on there. It's jumping by 2s consistently. Why do you think that is? Let's have this timer go a little bit quicker. Let's have it fire every 0.1 seconds. Let's pause it. Still, same number? Let's have it fire every 0.01 seconds. Same number? Does this seem like it's any faster than it was just a second ago? Why is that? We've told this timer to go at a certain speed, but the timer has to be implemented in terms of the game loop, how often things can update within the game. Okay, so there is a maximum speed that this timer can go, regardless of how often we tell it to operate. Also, all of these actors, at least actors of the same type. So for instance, These two guys are both of type flame turtle, so they're operating within their own thread of execution. So even though each of these has their own timer and each of these is making a change, what it's doing is it's going through the list of actors and say, display count, run your timer. Display count, run your timer. Display count, run your timer. Going back and forth between these two actors. Okay, so this actor displays its count, runs its timer, which adds 1 to count. This guy should display count, which is, in theory, 1 bigger than it used to be, right? Then he runs his timer. This guy should display the count. So if that were true, if that's the way it worked, if it literally went back and forth and did the entire behavior list for these guys, they should be one off. They should be staggering their counts, correct? Okay, but we're not seeing that. What we're seeing is the actions. This gets back to our idea of when do actions happen. Remember, display text is a behavior of type persistent behavior. So this happens once and sticks. This guy only updates under certain conditions. Okay, that way we don't get the flicker. Remember we were talking about that last time? So when we first display count, this count will not update until something causes it to update. So if we just say display the word hello and leave it there, we're not going to see the game loop flickering hello over and over again. Hello is going to be persistently there until something causes us to think we need to change it. Okay? That something is the game loop. Text can only change as often as the game loop runs. That's the fastest text can ever change. And however fast that is. We see it was less than this. We can kind of get a feel for the game loop if we say 0.1. We see that guy counting. Now let's change it to 0.01 and see if it goes a little quicker. Seems like it's going a little bit quicker than it was before. Okay, so somewhere in that range, we know we can at least go at that speed. We keep adding zeros on, or we instead of saying 0.01, we say 0.05, something like that. If we see some wiggle room in that speed, then if we slow down a little bit, then we'll have an idea that kind of where that game loop is running, at what speed. We'd have to kind of make a guess in there, but it's running faster than once every 10. It's running faster than 10 times a second, and seems to be running as fast as 100 times a second. But I believe we saw that it's not running as quickly as 1,000 times a second. So that feels about the exact same speed-ish. As this. Seem to be going roughly the same speed. Okay, so goes at least every 100 times a second, but not as fast as 1,000 times a second. Somewhere in the middle, probably. Okay, so this text can only update as often as the game loop runs. Now, each of these timers is set to run. Now, if you were designing GameSalad and you have a group of flame turtles and each of these guys has a timer associated with it, can these timers be offset? And what I mean by that is, let's say actually, this will be a fun way of doing this. We're going to have this timer run. So up to this point, we've always looked at variable stuff over here, attributes. Well, we also have some built-in functions over here. And one of these functions is the ability to generate a random number. Okay? And I'm going to generate a random number between 1 and 3. All right, and we're going to hope that we don't get the same random number there for those two. In fact, actually, let's spread that a little more. Let's say 1 and 10. So that means every single one of these flame turtles has a timer associated with it. But that particular timer will fire every some random number between 1 and 10 seconds. Okay? So when we run this, come on. What does that show us? Does it appear like they have the same random number? Is it changing at the same time? Let's print out the random number. So we're going to add an attribute to our flame turtle. We'll call this guy myrand. Okay. And what we'll do is we're going to change an attribute. We're going to change myrand to be equal to a random number between 1 and 10. Remember, this is back to learning to play within the matrix. Our timer now is going to fire every myrand number of times. All right. And what we're going to do is instead of showing the game count, we're going to show myrand. All right. Change attribute happens one time. It's an action. Happens exactly once. So each instance of flame turtle should generate a random number between 1 and 10 stored inside of myrand. Then its timer, when it gets created, will get created in terms of that variable. And we're going to make each of our flame turtles show the value of myrand so we can see what they came out to. Different values, right? Now we happen to know, it's been 3 seconds at least, right, that those timers have fired. Has that action occurred again? I didn't generate another random number, did I? Okay, but certainly these are different random numbers. Run this again, you see that we get new random numbers. Run this again, still new random numbers. Okay, so we feel confident that we're getting different random numbers with those guys. All right. So that's proof to us that each instance, each version of flame turtle gets its own myrand variable, and it's getting a unique value, at least potentially a unique value. We might roll the dice and get 2 7s, but we have the potential of getting a unique value. So now instead of saying myrand, we're going to go ahead and we're going to print out the game's count. All right, our timer fires every myrand number of seconds, and we'll increment the game count by 1 each time. Guys are still in sequence, right? And let's run it a couple more times. Clicking a little bit faster now because one of those guys had a faster timer. Okay. Now, what I'm going to do here is we're going to hit this checkbox that says run to completion. We want to see if that makes a difference in this behavior. Same exact behavior. Okay. Run to completion deals with what's happening inside of here, because we could have timers inside of timers. So we're saying that anything that's inside of this container, because a timer is a container, needs to finish in its entirety. All right. So that means if we have a timer inside of here, we want that timer to finish. even if it gets cut off in the middle, like the actor dies, something like that. If the actor dies, we still want, maybe it's that actor setting up a global variable somewhere. We want it to finish doing the math associated with that global variable. That's what run to completion does. And we'll see examples of that. But we're still set in this problem where we know that these guys are potentially getting different random numbers. Therefore, the timer for each of these guys must be based on a different random number. And we're running every so many seconds. And what are we doing every so many seconds? Well, we're incrementing the value, and then we're relying on the text to be displayed up here. What would happen if I displayed the text inside the timer? Okay, still in sequence. I'm trying to force one that shows up different. Probably force it this way. Hey. 1 to 100 is going to be problematic. What we really want is we want one of these guys to be fast and the other one to be slow. Here, let me put the timer up there. So we're going to do game count, followed by a colon, followed by flame turtles Myrand. So this should show us what the random number is for each of these guys after the first time it fires. Oh, hold on. I need to. We'll just turn that off for right now. What are we seeing happen here? Go ahead.
Well, I was just thinking, since it's a game attribute, and since they're both running the same kind of program, couldn't they be working simultaneously because of the same program?
Well, we're actually seeing some evidence about what's happening right now. What's happening on the screen right now? Just keep watching it. You'll see a flicker. See the flicker? So it seems like maybe the current random number is 8 or 9 seconds, something like that. Since it's not happening too quickly, we run it again. Maybe we'll get some better flickering. Yeah, there's some better flickering. Now, did you notice this guy's flickering more quickly than this guy? So they're clearly running on separate timers, right? Now you mentioned something about, well, they're both displaying count, right? Okay, whenever count changes, whenever that variable changes, we see the updated version, all the display texts. I know we're out of time here. Is it possible that they were showing different values, but only for a flicker? Most of the time we're seeing the set value of count. Does that make sense? Okay. The proof here is that when we say display text, that's only happening right now inside of our timer, not as a global behavior of this actor. So we're only seeing text during each firing of the timer. All right, we'll pick up there next time. You'll have an assignment next class that's going to be based off of this stuff, but you'll have a weekend to work on that.